I'd like to introduce Filippo Costa, that he will talk about Rust APIs for performance and tape safety, a case study. Thank you very much for being here.
Hi. Hello, everyone. Welcome to Rust APIs for performance and type safety, a case study. We're going to talk more in particular about FIX, which is the Financial Information Exchange Protocol. And I'm going to share with you some ideas that I have about a possible implementation in Rust of such protocol. So, anybody heard of FIX, maybe? Anybody worked with FIX? Yeah, it's quite niche, right? So, and we're going to focus really on public crate maintainability. So I would like to know how many of you maybe have published some crates on crates.io and they maintain it and it's used in production by others. Okay, like 3 people, right? Right. So I'm Filippo Costa. I work at Agenode. I'm based in Pisa. I work remotely, and I get to write a lot of Rust at my day-to-day job. So really lucky. And really, I would like first to understand why we care about FIX and why it's important to have a Rust implementation of the protocol. It's the lingua franca of the electronic trading world, really. Everybody uses FIX. So if you ever buy or sell shares on NASDAQ or the Milan Stock Exchange or London, chances are you're using a FIX implementation under the hood. So maybe even in your browser, there's a JavaScript implementation of the protocol, or maybe the browser is talking to the server, and then behind the hood, basically someone has implemented FIX, and they're using it to talk to the actual stock exchange APIs. So there are some public, some free and open source implementations of FIX in other languages, like C++ in Java. QuickFix is a major implementation. Everyone in the industry uses QuickFix unless you have very particular needs. So we would like to have the same thing in Rust. That's why we want to have something basically native and rather not port something or have just a thing wrapped around QuickFix. We want to have something that feels really native. So I feel like that's important, and the community really feels the need for such thing. So I'm gonna then introduce FIX, since most of you don't know much about it. We're gonna basically go through the protocol, the basics of the protocol, and what we need in order to implement it. And after describing the protocol, maybe we can start building something, and it's not going to be the full thing. We're not going to solve the problem of a missing Rust implementation of FIX today on stage, but we're going to focus on the APIs, rolling, not the function bodies or the just the type signatures, mostly modules, stuff like that. And hopefully we can have some ideas that abstract over the problem at hand, and maybe some ideas about public API design in general. But really, this is a case study, so we're going to focus quite a lot on FIX. So this is the project that really started it all. A few years ago, some guy started working on FixRS, which is still to this day the major FIX implementation that people use, or rather that people adapt from, because it's not really usable in production. It's incomplete, it's unmaintained, unfortunately. And the project was abandoned because the author felt like Rust wasn't mature enough or powerful enough, which really says something about the failure that we have maybe as a community to showcase what the language is capable of. If someone feels like they can't implement something in the language and nobody for many years has come around to actually do it, maybe there is something there worthwhile exploring. So that's really the project that started it all. And after that, there's been a few minor attempts, again, at building a Rust implementation. 2 years ago, I would say I started my own experiment with it called Ferrum Fix. It's not as maintained as I would like, but it does some cool stuff, and I've learned a lot of stuff doing it. So most of the code examples from the talk are going to be borrowed from that project in particular. So we have to talk about FIX and what it is, and we need to understand it. So again, it is the lingua franca of the electronic trading world. It is quite a recent protocol in the grand scheme of things. It was introduced in the 90s and popularized after the year 2000, generally speaking. There are still some venues, some individual stock traders, really algo traders mostly, that still to this day don't use Fix and they use more outdated protocols. But Fix is generally the state of things. Now, there are other advances like Nasdaq, Ouch, and each other protocols, which we won't talk about today. But Fix is generally what you have to do, what you have to implement, and what you have to know if you want to work in this field and you want to basically do electronic trading using the public APIs offered by these stock exchanges. And it is a human-readable and quite simple on the surface protocol, really. So the way fixed messages are composed, they are sequences of tags and values. So the tags are positive integers. They fit in 32 unsigned bits, really. So no need for more space. Then you have an equal sign, then you have an equal character, and you have an arbitrary value, really. And between the tag equal value pairs, then you have separator characters, which can be either the vertical bar or the start of heading character, which is the one ASCII value. Now, in my examples, I may use the new line as a field separator, just because it's nice to see it that way. But you can see kind of how a normal fixed message looks like. So you have the numeric tags, and they are quite arbitrary. They don't look like anything significant. And then you have the values, and you can maybe understand some sort of the structure of the fixed of this fixed message just by looking at it. So we have the first field, for example, is the version string, so 4.4. Okay. Then we have the body length, which is in this case 148 bytes, sorry. And then you have the body, indeed, which is where the most of the interesting stuff really is. Now, the third field, which always has a 35 tag, in this case, it has the D value, and that tells us the contents of the body. So if that letter was maybe F or G, the highlighted fields would be a whole lot different. So maybe depending on what operation you're doing on the stock exchange or what kind of information you want to transmit, the contents would be wildly different. And finally, we have a checksum field, which is 3 bytes, and it's the sum of all the byte values that come before it, which is a terrible checksum function, really. You have some, like, the longer the fixed message is, the higher the chances that you have a collision, which is why in college you should take a statistics class, most likely, because it's interesting and useful to know about this stuff. Because, again, that's a terrible checksum function. And this is what it looks like if you go on some website and you go looking for a fixed dictionary. So for a reference of what the fields mean, you can click on the tags, and they also have a human-readable name. And then you get a whole bunch of documentation about the field, when you should use it, and why. There's a free reference online, really. You can find it. And there's many problems with Fix. It's quite bad that it's the best thing we've got. It feels daunting to work with Fix because on the surface, really, it is a simple protocol. But I'm going to explain maybe later why it's quite hard to implement it in a fully standard compliant way. And what many venues and players in the industry do is they basically have a subset of Fix that they care about, and they implement it as an internal package, an internal crate, and they don't care really about being fully standard compliant. So that's really where the difference between a private crate and a public crate really starts to be important. Because as a public crate author, you want to support all use cases for the protocol. You want to really have a powerful API that everybody can use. You can't just have a subset of the protocol that you support, or really you can have it, but most people won't really find it useful. And again, this is an example of why you shouldn't do things just because they look decent, and you should actually do things the right way. You can't have that kind of checksum because of the central limit theorem. And yeah, you should know this stuff. And they haven't fixed it, by the way. It's been 30 years ever since the 4.2 version, and they still haven't fixed it. So there is no updated checksum field. But anyway, here's an example of why parsing fix is really hard. Normally, the tags are quite simple to parse, but you have two exceptions really. The data and length tags. You can find an example right there on the top, and then groups on the bottom. So in case you want to have a value with that contains the separator character, normally in a sane protocol, you would simply escape it, right? Like you do in JSON, in many other formats. Now in Fix, you have to include like another field before it, and then you have to tell whoever's sitting at the other side, basically, the length of the next field. And then they have to do some special parsing. So really have a regular language, something that could be a regular language that turns suddenly into very complex parsing. And the group aspect, group tags basically turn what would normally be an associative map into a tree, really, because you can have multiple instances of the same key, and you can repeat them if you want to have some stratified information in your fixed message. So you can reuse keys, and you can't just use a hash map, really. So these two aspects quite complicate implementing the fixed protocol. Sitting on top of the fixed protocol, we have the fixed session layer. So you have these weird diagrams which we won't really explore because the talk is not about them. But basically, these describe the kind of flow of information that you have between the client and the server. But again, we may leave this to the create users to just implement it themselves because it's quite user specific, and there's no use case general enough, really. So we're gonna leave that aside. And we can start thinking about what an implementation would look like. So we want to build a crate that we call fixed toy, for example. And you want the ability to parse fixed messages. You want to deserialize them, maybe some error checking. Then you want to serialize them as well when you have to send responses back to the client. Generally, these two things are all that's required of you. However, they require quite a lot of intricacies and subcomponents that we're going to take a look at in a moment. On the surface level, this is what you have. So without thinking about groups, the stuff that I mentioned before that really turns the associative maps into a stratified data structure, so a tree, you have just a hash map, you have U32s as keys, then you allocate a bunch of byte vectors, even though that's wildly inefficient. For now, we won't talk about it. And those are the values associated with the tag. Then you can parse the fixed message. You can try to. You can have some error, right? And there's a few problems with this. Well, it's not standard compliant because we're not dealing with data and numbering group, which is the group special tags. We don't know when we parse inside the parse function. We don't know as we find the tag whether to treat it as a normal tag or maybe a data or group tag. So we really need a subcomponent to tell us how to handle those special tags. And normally when you implement a data format like maybe JSON or anything else really, or TOML, when you implement assert the traits, basically, you normally don't care about streaming because you have an underlying framing mechanism that handles that for you. So maybe that your payload is in an HTTP response, so you know where it starts, you know where it ends, and you don't have to care about those things. You just have a byte slice or a byte vector, and you simply parse it. Now, Fix also has a way to you do streams with Fix. So you're not using any underlying framing mechanism. So you have to know for yourself when a fixed message starts and when it ends, and that requires some additional work that we're going to take a look at later. So these are the two main problems. There's also some other considerations that we can have. For example, getting fields out of this data structure can be quite hard because you're using numeric tags. And normally when you write code, you don't want to say, give me the 35 field of this data structure is just not really readable. So ideally, you would be able to use the text readable, the human readable names that we looked at earlier on the online reference. That'll be the ideal solution. Then you have some efficiency considerations as well. Firstly, you're doing a bunch of allocations when you parse this message, and most fixed users really want their software to be low latency and really, really fast. So you have to really minimize allocations. There's a bunch of enterprise fixed implementations that do either 0 or 1 allocations per message, and you really want to keep it low to a minimum. So if we want anybody to use this crate, we have to do that as well. So in this case, we're allocating the hash map as well as all the byte vectors. And then finally, hash maps in Rust are quite slow by default. The underlying implementation of hash map is really, really fast, but we have hash-toss resistant build hasher implementation by default. So you can select a different hashing algorithm as an additional type parameter in the hash map. And ideally, we want users to also possibly choose that, because they may not care about hash-toss in their situations, and they can use whatever hashing algorithm they want. So these are the problems that we have with this very basic solution to the problem. And the first solution that I'm going to propose here is to leverage the fixed dictionary. Now, the fixed dictionary is something that the fixed protocol authoring body publishes for every single fixed version. It's available for free on the website, and it is an XML specification, wonderful XML specification of what the tags mean, their data types, so whether they are simple strings, maybe they're groups, or maybe they're data. So that kind of information is really useful to us, and we need it in order to parse correctly all fixed messages. And then you also have a section that tells you about messages. So whether the third field has a value of D, like the one we saw earlier, then you can expect these fields to be in the data in the fixed message that you're going to parse. So for now, we're just going to focus about the data types of the fields that this specification includes, because it's what we're going to need in a second. And I want you to take a look at the indentation level right there. That's a specification for a group, and that's what you have to know in order to correctly parse that specific field. You have to reserve maybe another instance of fixed message, and you have to put all the nested tag value pairs in that other fixed message. But anyway, again, focusing on the fields section right here. So we have to parse it, and this is just a metadata data structure, something that we don't really modify once it's created. So we just keep it around. Usually you have that XML specification at build time. Sometimes you do get it from the client or the server at runtime, but usually really you can do this stuff in the build script. So we're just gonna have an in-memory data structure that keeps a hold of all the field specifications, what tags we can expect, their data types, and it's quite expensive from various points of view to have this, to keep this object around and to use it. So to maybe query whether there's a field with a specific tag or a name, it's quite expensive both to create it and to query it. But still, this is something that we can have for now, and it works. So you have the full XML specification available to you in Rust code. So that's great. And so at this point, what we would do is we would take the parse function from earlier, and we would simply add reference to the dictionary so that we can, every time we meet a tag, we can see whether it is a data tag, a group tag, or a normal tag. Now, what I told earlier about the human readable names as an alternative to numeric tags can really be useful here, because if you keep the dictionary around in your fixed messages, so you keep a reference as an arc inside your fixed message, every time you use one of the getters of the fixed message struct, you can then query the human readable name inside the fixed dictionary, and then you know the numeric tag associated with that human readable name. So basically, we won't take reference, we're going to take an arc, and that way we can embed an arc dictionary inside every single fixed message. And the dictionary struct is quite heavy, again, and ideally, we wouldn't want to burden the user with such a huge data dependency, but for now, this is what we have, and we're going to take a look about how we can minimize those dependencies later. Now, going back to the streaming support problem, it's a bit of a problem to have that ideally you would leverage existing crates to solve, because otherwise it gets really messy real fast. So you would use the Tokyo codec utilities, the bytes crate, which is really useful for dealing with networking without allocating a bunch of bytes every single time you have maybe the field values. So you can use these two crates, and I'm sure most of you have. These are really useful, and we're going to take these as a reference point in our implementation. So we have expanded the parse API to take a dictionary arc. Then we know that we're going to add streaming support using Tokyo. At this point, there's a few problems. So the API is more powerful, really, but what you're doing is you're making it vastly more complicated. So every single user needs to care about these things because the API has changed. So even users that only cared about the initial subset, they didn't care about data or group tags, they suddenly have to care about the dictionary, which is not a great thing, really, because it seems quite gruesome to build a dictionary from an XML specification that you have to fetch from the web, even if you don't care about it. So there's a few problems here where we are really complicating the API. Also, now that we're using bytes, because we need the streaming support, you can't just have an example file where you just use a vector of bytes or a byte slice. So you have to use the bytes crate, really. So that dependency is brought over to the users as well. And ideally, we would be able to abstract over it. So once you do all of these things, still there's a few other missing pieces, and those would add many dependencies as well. For example, if you want to implement the fixed session layer, then you have to suddenly add support for the OpenSSL crate or RustLS. And many fields are going to be decimal values, and you don't want to parse them as floats because they lose precision. So maybe you would add a dependency to a decimal crate, and all of these pollute your public crate API, which is, again, not ideal. So whenever you find a solution using a concrete type, and that may add some unnecessary dependencies onto your users, which ideally you would be able to avoid, well, you can abstract over these types with traits, which are the most powerful type abstraction mechanism that we have in Rust. So ideally, you would be able to replace many of these type dependencies with trait implementations. And sure enough, you can do that. So for example, we can have a trait that abstracts over the dictionary, and maybe if you don't care about the XML specification, sure enough, you can just have an empty implementator of the isDictionary trait. And the fixed message now with this modification can now take a type that implements the isDictionary trait. And sure enough, you can also abstract over the bytes type. So even if you don't care about streaming support, maybe you are using fix in a specific instance where there's an underlying framing mechanism that helps you. Well, you don't really have to care about add the streaming support because there's, in this case, something that can be referenced as a byte slice. So this is kind of the general direction where we're going. And you don't need to do this stuff when you are building maybe an internal crate inside your company, someone that your colleagues might be using. But this is really the crux of the issue here, that when you're building a public crate, you're forcing downstream users to use the APIs that you build for them. And they're not really going to fork your project if those APIs are not easy to use. Maybe a colleague of yours for an internal crate, they might just push commit and be done with it. But generally, you have a never increasing feedback loop distance between users and crate authors. So you really want to make sure that your APIs are easy to use for everybody. Otherwise, you're forcing them either not to use the crate or to fork it, really. So obviously not ideal. And after taking a look at what we can do with the dictionary dependency, we can abstract over it with a trait implementation. We can do some more work around it. So going back to the fixed message struct implementation, we would then, after parsing it, we would then have getters around it. So we can get the value of a specific tag, etc., etc. And there's some trait ideas that can help us here. So let's say that your tag is supposed to have a numeric value. So after the equal sign, you can expect a numeric value. Well, then you can implement a trait, and you can get the value of a certain field as decoded by some certain code, which is the implementation of this trait. So this trait really lets you define a type, a fixed type. So I'm mapping from a Rust type to a fixed data type. And using an implementation of this trait, you can deserialize whatever field as you want by selecting the type parameter. And you can do some simple deserialization over it, or maybe if you have some particular performance needs, you can have some lossy no error checking, basically deserialization. No unsafe really, but no error checking. So for example, let's say that you're decoding the value associated with a tag and you're expecting a number. Maybe you don't really care about detecting whether it's a valid number or not. Maybe you just want the correct value as fast as you can. And if whoever is sending you that data, they messed up and it's not really a number, well, you don't really care about detecting that, maybe. So we can have several both serialization and deserialization modes here. And this kind of trait really helps us make the API so much nicer. And we're going to see it in a second. So after you define this trait, then you need the getters from the fixed message struct. And you can either just get the raw byte slice, or you can maybe decode them using the trait that we've just seen. So you can select indeed the type parameter, and then in the function body, we're gonna decode that fv underscore raw value using the deserialize method that we saw in the trait earlier. And the API that you see with these two traits put together actually looks really nice. And this trait field map is simplified. There can be other getters. So maybe fv underscore the opt, which stands for field value optional, that maybe doesn't return a result. It can give you an option in case you're not sure you want that value or not. Maybe it's there, maybe it's not. You don't want, whether it's not present, you don't want to get an error, you simply want a none. So we can get something like this out of it, which looks really, really nice. And in this case, fix42 is a module that contains some code that either we've written or we've auto-generated from the dictionary struct. And all of these types, all of these arguments to the fv method, they take implementers of the trait. And suddenly you don't even have to specify what type you get out of it, because there's Rust type inference helping us out. And this is quite nice. This is not kind of API experience that you get out of QuickFix or QuickFix-J, which is the Java reference implementation. So by leveraging the trait system and putting the work clauses at the right spot, it can really help Rust to give you nice type inference for free in these situations. So now you can go overboard with it. This is an example of the Diesel API. Sometimes you have these weird, very complex where clauses that are very messy to deal with, and they give you nightmarish compiler errors. But on the other hand, they can really help you out when you, for example, do a breaking change. So I've recently been migrating our main code base over to Diesel 2.0, for example. And even though some of the concrete types changed, sometimes there are some trait implementations under the hood, which are private in the diesel modules, and you don't even know about them, but the work clauses take care of everything for you. So really, you can go overboard with it, sure you can, but most of the time, adding work clauses with the right traits really helps your users, because they let you define exactly what you need. And you don't just depend on a concrete data type they may or may not like. So they're not all powerful, surely. There's several important limitations to the Rust trait system, and there's a lot of work in the background from many people from the compiler and language teams to basically increase the kind of API service that we can specify with the traits. So we were talking about GATs earlier, a few talks ago this morning. There's async offense inside traits, which are related. And there's a few other limitations that ideally would let us specify more things using traits. One of the main ways you can improve your Rust expertise when you're writing public-facing code, and you want to do some weird type and trait magic, is to know beforehand and to have a sense for when things are not going to compile, and you're gonna find maybe a missing feature in the language. So maybe before you actually write the trait definitions, 2 or 3 trait definitions, then you may realize beforehand that eventually you're going to have to deal with missing genetic associated types. And if you can feel that and understand it beforehand, you have a better understanding of the kind of API that you can specify using Rust without actually going every way, trying everything and see what it sticks and what the compiler basically is happy to compile. So again, limited trait system, but already what we have is quite powerful, and we can do some really cool stuff with it. So when you're writing internal crates and private code bases, what you do usually is you only use traits if you need to abstract over some concrete type that you have, maybe because you want to do some code reuse. Really, that's the main use for traits. Now, going back to the difference between private crates and the public-facing crates, the difference is quite striking. When you are proactive about the use of crates in crates that you publish free on the web, you're going to do a favor to your users, because they can really implement those traits in the way that they see fit, even in ways that you didn't quite foresee. And I think there's many striking examples in the Rust ecosystem about powerful traits that from famous libraries and crates that you can implement your own way. Even though in the library itself, there's maybe 1 implementation or 2 implementations. So something that you could do either a concrete type or an enum maybe. So you can be really smart about this and be so much more proactive and use traits even if you don't think there's going to be a need for it, because your users might have different requirements from you, and if you didn't think about it beforehand, well, now it's their problem. It's not yours anymore, and that's not really good if you want to do a favor to your users and you want to have a nice API experience. So we can really postpone decisions using this kind of approach. When you define the traits and you let your users define it, maybe with some good high-quality default implementations, you can be quite agnostic towards their use case, which you don't know much about usually. So I feel like that's a good habit, and I would like to see more adoption of it in the Rust world. So more traits, even when they're not necessary in public code, because again, it's not the same as a private trait. And this actually turns into a problem for some crate authors, because they feel like if they define many traits and they add unnecessary structure, even when they don't feel like there's a need for it, well, then they're resistant to breaking changes. Because they know that eventually down the road, they're going to have to change that trait definition, something that they could have done themselves using without breaking the public API, were it a concrete type. So they actually resort to zero-based versioning, which is technically semantic versioning adherent and compliant, but it doesn't really do anybody a favor because it doesn't give you any useful information about the crate versioning. So don't do this. Definitely use traits even when you don't feel like it's necessary. And well, yeah, increment a major API, implement a major version. It's not a problem. I feel like people feel like there's going to be something bad happening when they hit 1.0. Suddenly they can do anything. The crate is frozen. It's not like that. You can just increment the crate version. It's okay, really. Nobody cares. You can just have to change in the cargo.toml. You just change the crate version, and it's okay. So there's many crates that do this, many others that don't. But I feel like there's virtually no difference between using 0.28 in a crate rather than 28.0. If anything, the later gives me more available information about the history of the project, breaking changes. It's just a good habit, honestly. And going over some of what we've said. So the kind of nice API that we saw in the example earlier is only possible when you do some maybe code generation from the dictionary trait. So again, there may be something that you don't want to do in your public trait, maybe because it's too hard, maybe because it's too difficult. You don't want to deal with code generation, but your user certainly can. And if your automatically generated types implement something looking like its dictionary trait, well, they can do that only for the added structure of the trait that you introduced, even if beforehand maybe you wanted to use the dictionary concrete type. So there's another use case here. I've only shown you the tag value pair syntax for the fixed protocol. It's not the only one, unfortunately. There's the JSON, there's a mapping between tag value pair syntax and JSON messages. Then the fixed protocol authoring body, they've also, they wrote some documentation on how to express fixed messages using protobuf, ASN.1, many other formats, in the hope that maybe one of them is better than the others, but really you just have to do one the right way. But still, if you have these traits, then a downstream user may add support for fixed messages as expressed from JSON or protobufs, and they can map easily from the traits and the types that you provided. Now, when you go overboard with this, sometimes you have trait overload. So maybe you have dependency, you have many type parameters in your structs. That's no nice API to use, really, again. So sometimes the approach that you can take is you can have a filler trait, some sort of surrogate, this is what I call it, and this is a decently common pattern. And the only purpose of the trait is to reduce the number of type parameters, and then you can use associated types inside the trait, and your users can either use a good default trait implementation that you provided, or they can simply fill your own in the associated types. And ideally, default associated types actually would help us here. They would provide a nicer experience. So this is a pattern that can be really useful if you go a bit, maybe too far with this. So this is it. And thank you for listening. And if you have any questions, I'll be happy to take them.
So thank you very much, Filippo. And if there are any questions there from the audience, yeah.
Hi, just a simple question. Why using a dictionary approach in Rust when you have, for example, macros or anyway, the ability to define the full message with the full field names and therefore a full validation of the message given, but not by assessing every time the dictionary telling is there that either, is that the field, is that there present the checksum, but having the type doing that.
So basically you're talking about code generation not only for field types but messages as well. So every maybe auto-generated message type would have its own parse function implementation, and that would I'm not sure what your what your proposal is, because
Yeah,
there is,
for example, a type of a message of fix 4.0 that is the full fields of the message. Okay.
absolutely, yeah. So you can now, the problem with that is so with that approach you could have like struct incoming order, I don't know, something like that, and then you have the fields with the specified types that implement the trait that we've seen. Sure enough, you can do that. It can be quite hard to have nice API coming out of it, because many users, when they read the fixed message, they want to deserialize the single fields as they want to. So some user may want to deserialize a single field as a string, some other as or rather, maybe as a decimal, maybe as a Rust decimal, which is another trait. So it can be quite hard to do that. But again, if you expand on the code generation aspect of it, you can indeed code generate also fixed message specific implementations from the dictionary, and at that point the whole thing becomes a fully built-time dependency. And ideally, this is where we would go if we had a nice and open source fixed implementation in Rust.
Thank you. Another question there.
Hi, thanks for the talk. If you want your users only to depend on trait types, does it also mean you have to provide factory methods for all of your types, or are there other approaches?
I don't think I'm seeing a factory or builder pattern requirement here. You just need, well, maybe something that implements the dictionary trait, is dictionary trait, and then you have dictionary new, for example. So where in the
No, my question was, how do the users construct the concrete value, the concrete struct, basically?
So sometimes you can acquire default, and that's quite a common pattern. If if you can basically reason about the whole thing and basically assume that trait implementations have a default sane implementation. So in those cases, you would use default. Some other times there is maybe something builder trait that has as an input the information that you think users might need to construct that type. And some other times you have a way to inject that dependency, and the users can use whatever builder or pattern that they want.
Okay, cool. Thanks.
Thank you. Any other question? Yeah, there.
Hi, I have a question about how Rust can help you protect your application when you may be subject to serialized attacks on the format. Since you have a data format that has a separator and strict rules, is it in your experience that the Rust type system helps you protect the application from possible attack on serializer and deserializer?
So for example, in some cases you may have the separator inside well, in that case, the parser really would simply hit that and assume that's the end of the value, and then it would keep parsing, and it would be invalid because generally you would have garbage after it, or it simply may not pass the parse function validation logic. So generally, no, I wouldn't say that's a problem. In some cases, if you want to do some, maybe add, like make the Rust type to fixed type trait, if you want to make it unsafe, to make things speedier, because maybe you have you have a trustworthy relationship with whoever is sending you that data. Maybe you're going to get fined if they send you bad data, so you don't really care about validating it. That's quite a common pattern. So in those cases, certainly there are security implications, but relating to the separator in particular, or with the structure, the syntactic structure, no, I don't think there's any problems there.
Thank you.
Thank you very much. Okay. Is there any other question for for Filippo? No, so I think I can thank you. Thank you very much.